This lesson is about defining and using sequences in series. A sequence, as you can see here in this key concept box, will give you the definition. It's a sequence is a function whose domain, that's all the set of input values, is the set of consecutive integers. Consecutive integers means one right after the other. For example, 1, 2, 3, 4 would be consecutive integers. If a domain is not specified, it is understood that the domain starts with 1. The values in the range are what we call the terms of the sequence. And here you have an example. So your domain are your inputs, so 1, 2, 3, 4. And in general, we just call this the nth term. So your range would be a sub n, so that's a subscript, a sub 2, a sub 3, a sub 4, and then a sub n represents the nth term in the final sequence. A finite sequence is a limited number of terms, so it actually stops. An infinite sequence continues without stopping, and here you see that we have two examples. So a finite sequence, 2, 4, 6, 8, and there is nothing else beyond that, and an infinite sequence, 2, 4, 6, 8, and then you have your ellipses, the dot, dot, dot. A sequence can be specified by the equation, or what we call a rule. For example, both the sequences above are described by a sub n, that's the general term, is equal to 2 times n. And then again also f of n is equal to 2n. Typically in this unit we will write it as a sub n is equal to 2n. For this next problem, it says write out the first 6 terms of the following sequence. So a sub n is equal to 2n plus 5. So the first one I'm going to find is a sub 1. So that means that your n value in this one happens to be 1. So I'm going to substitute 1 in place of n. So you'll have 2 times 1 plus 5. So a sub 1 is equal to 7. And then a sub 2, now our n value is 2, so I'm going to substitute 2 in place of n in that general equation. 2 times 2 plus 5. And that will give you 9. A sub 3 would be the third term. So 2 times 3 plus 5, or 11. A sub 4 would be 2 times 4 plus 5, or 13. And a sub 5 would be found similarly. 2 times 5 plus 5 is 15. And then the last one, a sub 6, is equal to 2 times 6 plus 5, which is 17. So they would represent the first 6 terms of this sequence. This next problem we're going to work pretty similar to the last one. So a sub n is equal to the quantity negative 3 times n minus 1. So I'll find my first term, a sub 1, and my n value is 1, so negative 3 to the negative 1 minus 1. Oops, that should be a positive 1. 1 minus 1. So you have negative 3 to the 0 power, and anything to the 0 power is just 1. Then my second term, a sub 2, is negative 3 to the 2 minus 1. Negative 3 to the first power is negative 3. And I'm going to do that for the remaining terms. You might want to pause the video, go ahead and find the remaining terms, and come back and see if you have it correct. And here are my remaining terms that I found. 9 was a sub 3. A sub 4, the fourth term, was negative 27. Then 81, and then the last term of the first 6 would be negative 243. Now for part C, again, although it looks a little bit different than the last two, we will find those exactly the same way. So we're going to go ahead and find a sub 1 So that means our n value is 1, and we're going to substitute a 1 in for both of the n's that we have here. So that would be 1 divided by 2. A sub 2, now my n value is 2. So that gives you 2/3. A sub 3 is 3 divided by 3 plus 1, or 3/4. A sub 4 is 4/5. And the fifth term is 5/6. And then the last of the first 6 that we were told to find would be 6 divided by 6 plus 1, or 6/7. For this next section, we're told to describe the pattern, write the next term, and then write a rule for the nth term of the sequence. So in part A, I noticed that -1, 8, 27, and 64, I recognize those as all my perfect cubes because 1 is 1 cubed, 8 is 2 cubed, 27 is 3 cubed, and 64 is 4 cubed. So the pattern that I see here is that they are all perfect cubes. So the next term, so right now what they're giving us, a sub 1 is -1, the second term is -8, third is -27, then -64. So then the next term would be your a sub 5. So the next one would be 5 cubed, which is -125. Now they all happen to be negative, the n value cubed. So for example, this is my first term, my second term, my third term, my fourth term. So if I take a look at my n value here, n is 1, and that's -1 is the first term. My n is 2, that's -8. 3 is n, -27. So it's essentially this n value, but it has to be a negative. So the general of this would be -n to the third power. It's the opposite of n cubed. For this next problem, I'm going to go ahead and list out my terms. So a sub 1 is 0, a sub 2 is 2, the third term, a sub 3 is 6, a sub 4 is 12. The pattern that I notice is that here, between 0 and 2, I'm adding 2. Between 2 and 6, I'm adding 4. Between 6 and 12, I'm adding 6. So I notice that I'm adding 2 more to get to the next term. So for the next one, I'm going to have to add 8 to get to a sub 5. So that means that a sub 5 would equal 12 plus 8, which is 20. Now the pattern for this one is a little bit harder to notice because it really has nothing to do with that general term that we just found, the adding 2, the adding 4, 6, and 8. So the easiest way that I think to do this is to take a look at this n value, and you really just have to kind of think through this and try different things if you don't see it right away. So our n is 1, and our a sub 1 is 0, and then 2, 2, 3, 6, 4, 12. You kind of have to look at the n values, these subscripts, and see what you could do to that n value to get to the term that's underneath of it. So in this one, there's 2 different ways that you can write this answer. You can write a sub n is equal to the term number times the term right before it. So for example, if I take a look at this number 12, this 12 is the 4th term, so it would be 4 is the n value, and then the one right below it is the 3rd term. So if you do 4 times 3, that would give you 12. If I looked at the 6, to get the 6, I would take that term number, which is 3, times the term number in front of it, which is the second one. 2 times 3 is 6. So you could also see it sometimes as n squared minus n. So if you were to take the term number that you're at, 4, and square it, that would be 16, and subtract 4, again, that would be 12. So if you wanted to get 6, you would take that term number, which is 3. 3 squared is 9. 9 minus the 3 is 6. So again, it just a lot of times just takes some thinking through and maybe trying something, see if you can figure it out with, maybe guess and check. Now we're going to be looking at series and summation notation. So here we have when the terms of a sequence are added together, so that's going to be the difference that we see here with series versus sequences. The resulting expression is what we call a series. So if you just have a list of numbers in a sequence and you have commas in between them, that's considered a sequence. If you then go one step further and you have an addition sign in between the terms, that's what we call a series. A series can be finite or infinite, just as the sequences were. And here you have those examples, so pretty similar to the last one. You can use what we call summation notation to write a series. For example, the two series written, what we saw before, you have your 2 plus 4 plus 6 plus 8. And then here is what we call our summation notation. They say it over here on the left. When written in summation notation, this series is read the sum of 2i, so we're summing up 2i, for the values of I from 1. The lower limit is down here below the summation sign, so that's where we're going to start. And then the top number is how many terms we're actually going to do. So we're going to go from 1 to 4. Now, again, you can use any variable you like. Sometimes I is used. Sometimes you'll see k is used. So different variables are used. So don't be alarmed when you see something other than the letter I, as long as your variables match, essentially. And here we have our finite or infinite series, and that goes on forever. So if you look at the top portion of the summation notation, it does have an infinity sign because that goes on forever, so there is no top limit to the summation. In both series, the index of summation is I, and the lower limit of summation is 1. So down here it says 1 in both of them. And 4 is the finite, the upper limit of that. And the summation notation is also what we call sigma notation, because the upper Greek letter sigma is that capital E that you see right here. So that's also, again, let me write that in sigma notation. Now again, a lot of times it's just summation, so again, it takes a little bit of time to get used to drawing those summation symbols out. So for number 3, it says write the series using summation notation. So the first thing I want to know that my first term is a sub 1. A sub 2 is my second term, my third term, my fourth term, and you should again notice that 1, 8, 27, 64, 7, 29, they are all your perfect cubes. So your goal is to figure out, one of your goals is to figure out what cube 729 is. And that happens to be 9 cubed. So the last part, this is a finite series because it has an ending. And this is the 9th term in the end because 9 cubed is 729. So again, I know that these are my cubes. So I'm going to write I cubed. And then you're going to write your sigma notation. And then the lower limit, which is the first term. So I'm going to start at I equals 1. And then the very last term that we have, we go from 1, 2, 3, 4, all the way up to 9. So when we write this out, it would be, again, I cubed, so you would plug in a 1. 1 cubed is this first one that we see here. And then you go to the next integer, 2, and you plug in 2 for I. So 2 cubed is 8, so you're going to add on the next one. and then you go to the next integer, 3, and cube that. 3 cubed is 27, and so forth until you get to the very last one. In this case happens to be 9. 9 cubed is 729. Now for the next one, again, this is another one of those that you'll have to probably guess and check till you can figure out what the pattern is. So again, I'm going to go ahead and write down the term numbers at the top because I think that it's a little bit easier if I label those out. So again, this is an infinite series. I know it's an infinite series because of the ellipses here, the dot, dot, dots. So I'm going to take a look at my n values, which are the term numbers. So my term here is 1. So n is 1, and then that's my first term. And then you have your second one, which is 2, and that's 2. Now, it's a little bit different because you have your 3 here, and that's now 4. And then your fourth term is 1/8. So when you write your sigma notation on this one, again, you're going to start at I equals 1 because the very first term is 1. And I'm going to go to infinity because it's an infinite series. Now again, with some guessing and checking, this pattern turns out to be 1 divided by, because 1 is in the numerator of all of them. And this would be 2 to the I minus 1. Now again, you can write this as 1 over, let me write it off to the side, 1 over 2 to the 0 plus 1 over 2 to the first plus 1 over 2 to the second. 8 is 1 over 2 to the third. So again, labeling my terms. So in the denominator here, you'll see that you have 0 is the exponent of this denominator, which is 1 less than the term that we're in. The 1 is the exponent of this 2, which is 1 less than the term. 2 is 1 less than the third term. The 3 is the exponent, is 1 less than the fourth. So that's why I have I minus 1, because I'm 1 less than what term I'm in. Again, a lot of times it just takes some guessing and checking to figure out the right one. For these last problems, number 5, find the sum of the series, and we're going to sum up 3k squared minus 7, and our lower limit is 3, so that's going to be the first integer we substitute in, and then we'll substitute all the integers up till 5. So I'm going to go ahead and plug in k equals 3. K equals 3 would be 3 times 3 squared minus 7. And when I find that out, that gives me 20. And then k equals 4 will be the next number I substitute in. So 3 times 4 squared minus 7 is 41. And then at my upper limit, up at the top of sigma, it has a 5. So this will be the last number that I substitute in. 3 times 5 squared minus 7, which is 68. And then since we're using summation notation, we simply just have to add those numbers together. So when you add 20 plus 41 plus 68, you get 129. So that would be the sum of that series. And the next one, number 6, find the sum of the series. And the lower limit in this one is 2, and the upper limit is 6. So I'm going to start plugging in my k values at 2. So you'll have k equals 2, k equals 3, 4, 5, and 6. So when k is equal to 2, you'll end up with 2 squared minus 2, or 2. When k is 3, 3 squared minus 2, 7. 4 squared minus 2 is 14. 5 squared minus 2 is 23. And then the last one here for k is 6. 6 squared minus 2 is 34. And then we'll add up all the terms that we came up with, 2 plus 7 plus 14 plus 23 plus 34 for a total sum of 80. And the last part that you have to take notes on are some formulas for special different series that we see. So here if you have a sum of n terms of 1, so say you have the number 1 and you're summing it up, I don't know, 10 times, then the answer would just be 10. So because you'd have 1 plus 1 plus 1 up to 10, which would equal just 10. For the second one, the sum of the first n positive integers, so from 1 to n, that would just be n times n plus 1, all divided by 2. And then the sum of squares of the first n positive integers, so if you wanted the squares from 1 to 9, so the top limit would be 9, so you would plug in a 9 times 9 plus 1 times 2 times 9 plus 1, all divided by 6. So these are formulas that, again, have already been worked out for you. So instead of guessing and checking, if it asks for the sum of the first 10 positive squares, then you could just plug it into this formula.